All right. So we are now moving on to the second video, and we're going to be talking about the division algorithms, right? Those processes. We're going to get into long division. Maybe that's something that even when you hear that, you're like, oh, that's not my favorite thing in the world. As I mentioned in the previous video, division is often the most difficult and takes the most time in class to master. We don't, it's not quite as emphasized like it used to be for the, 4 or 5 digit long numbers, just because of the use of calculators. But we still have to understand the algorithm, how it works. You still have to be able to do it. And what we're really going to be focusing on in this video are the manipulatives. So what you're going to want with you now, if you don't have them, are the base 10, your envelope with your base 10 pieces, because we're going to use those so we can connect, again, the pieces to the algorithm, which then this one might be the hardest for, it's often the hardest to really see. And so we're going to spend some time digging in there. So the first thing I'm going to do is use base 10 blocks. And if you have it out, we're going to do 48 divided by 4. So what I want you to do, if you've got your base 10 pieces, is see if you can figure out what that might look like. If you're going to do 48 divided by 4, how might you use your base 10 blocks to do it? Okay. And maybe if once you found one way, say, is there even another way that I could use an arrangement of my base 10 blocks in some format to solve this problem, to answer this question? So pause and do that. So one way that you might have done it is like this. And notice how I say one way, because there are lots of ways. One way you might have done it is this. So notice what I have there. Look at the arrangement of the pieces. There's 48 pieces there, right? We have 10, 10 and 2, 10 and 2, 10 and 2, 10 and 2. So what do I have there? I've got 12 here, 12 here, 12 here, and 12 here. I took my 48 things and I put them in groups of 12, right? 4 groups of 12. That is an example of that sharing or partitive concept that we talked about, right? Where the 4, the divisor, is telling us how many groups. And then the answer is how many are in each group. Okay. So that's one way we could have modeled that using our base 10 blocks. So now try it again. And, or maybe you did it another way. Here's another way that you could do this same problem. Like this. I'm wondering if anybody did it like this. 48 divided by 4. Let's examine our 48. Let's examine our numbers and what they mean in this scenario. 48 divided by 4. Again, here's our divisor. What is the 4 telling us in this model? How many are in each group, right? There's 4, 4, 4, right? So we took our 48 and we separated it into groups of 4, not 4 groups, but groups with 4 units in it. And then we counted how many there were, right? So the 12 is the number of groups in this case, number of groups. And that's the measurement concept, right? So this is an example of the sharing concept. This is an example of the measurement concept. And I hope that you're now starting to see the difference between those two. Even though they give you the same answer, they're telling you something different about the scenario. Now, there's one other model that maybe some of you did. And we've talked about this in the multiplication section, and it might look like this. We did arrays when we were doing multiplication. And so maybe what you did was you said, all right, if I have to do 48 divided by 4, could I take my 48 pieces, arrange them in a rectangle where one of the sides of my rectangle is 4, and then count how many I have on the other side of my rectangle? 12. Yeah. And so this is another possibility. This is using the array method of division. All three of those methods work. Okay. Sometimes one may be more convenient than the other, or just works better than the other based on the scenario or the type of question. But they're all going to get you to the same answer. Is it important that students understand how all of them work? Yeah, absolutely. Now, one of the things you might even notice with the array is that, and I'll see if I can do a quick sketch. Actually, what I'll do is I'm going to copy. I'm going to paste this little diagram, and I'm going to do it a couple different times because I want to show it a little bit differently and connect it to the idea of the measurement and the sharing concepts. So you can look at these arrays two different ways. You could look at it as one group here. There's one. There's another one of 12. There's another one of 12. And there's another one of 12. So you can look at it as 4 groups of 12, right? Where you're looking at your groups as these horizontal lines. If you're envisioning it like that, that's an example of the sharing concept, right? This is telling us the number of groups, right? Or maybe when you were sketching your array, you envisioned it more in terms of columns. There's 4 here, 4 here, 4, 4, 4, and you just kept stacking groups of 4 until you ran out of those little unit squares. So in that case, you're sort of looking at them vertically, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what of the concepts is that? That's the measurement concept. So even within the array, you can still be using at those measurement or the sharing concepts, right? It's how are you viewing your rectangle? How are you viewing your array? Okay, so let's move on now to a more complicated process. And here's where we're going to introduce long division. So we're going to introduce long division. And the way we're going to do it is with base 10 pieces and the long division algorithm alongside it. Now, I would get out my own base 10 pieces and move them around, but I want to be able to write at the same time. So what I recommend that you do is have your base 10 pieces, do this along with me, so you can start to see it. Okay, so the problem we're going to do here is 378 divided by 3. All right. And so the first thing I want to talk about is when you use the division algorithm, you always take the dividend and put it on the inside and the divisor and put it on the outside. So whatever you're dividing by is always going on the outside. So that's the first thing that we do. Now, I'm going to take 378, and I'm going to just put the image of it right here so we can see what 378 would look like. And for some reason, I'm not able to. There we go. 378. So if you have your pieces, you're going to have something that looks like that. 3 flats, 7 longs, and 8 units. 378. And so what we're going to do is we're going to be using the sharing method. All right, we're going to be thinking about it using this method, right? Where the divisor is telling us how many groups we're going to have. That's how we are going to be thinking about it when we use this division algorithm. And so when you're doing long division, you are always taught to say, okay, how many times can this number go into this number? And we see that it fits in once. Now, it's so important that we understand what that number 1 represents. So I'm going to do it maybe in a way you haven't even seen before. What we're really saying is, how many times does 3 fit into the number 300? And the answer to that would be 100 times, right? When we put that 1 up there, it's representing the number 100. So I'm just going to write it as 100 to start. Then what do we do with our division algorithm? We take 3 and we multiply it by 100, and we write it below here, and we subtract. Now, maybe when you learned it, you didn't write those 2 numbers there, right? You just wrote the 3. I'm going to write the zeros there so we can really start to connect it with the division algorithm, the division algorithm with the base 10 blocks. So the reason that we do that is because we want to see, what do we have left after we've done 3 times 100 and we subtract, we see that there's 78 left. So let's connect this to our base 10 pieces. And so the thing we might do is say, all right, here's what that looks like with our base 10 pieces, okay? I can look at my, look at 3 of these flats, right? I can look at 3 of these flats, 1, 2, and 3, right? Each one of them has 100 pieces in it, right? So if I'm going to start to put these in 3 different groups, here's my first group, here's my second group, here's my third group. And that's where that 1 comes from, okay? 1, 2, 3, okay? 1 is representing a singular flat piece. Now, this stuff over here, this is what we have so far as a remainder, right? That's our 78, okay? And so what happens next? What happens next? If we are doing our traditional division algorithm, we would now say, how many times does 3 go into the next number, which is 7? If we're counting, 3 goes into 7 twice. Now, I already stuck a 0 there. I'm just going to cross that off and replace it with a 2. And I'm even going to write it as 20, because that's really what we're doing. We're seeing how many times does 3 go into 78. 3 times 20 is 60, which when we subtract, we get a remainder of 18. But what's really happening in our base 10 pieces? This is how you're going to want to be separating your pieces next. Again, we're putting them into 3 separate groups. If you look at these long pieces, right? And you say, okay, can I put them into 3 separate groups? Well, 1, 2, 3, right? 1, 2, 3. Each one of them would have two of the longs. Each one of them would have 2 of the longs. And so we shift them over to their own individual group. Here's group 1, here's group 2, and here's group 3. All right, we've now put 2 of the longs, which with each flat. Okay, and so the number that we put again up on top here is saying how many 10s are in each group. There's 2 10s in each group. 1, 2, 1, 2, and 1, 2. All right, what do we have left? We have a remainder of 18. Here's our remainder of 18. That's this right here, okay? So then our last step is to take these remaining pieces, 18, and put them into 3 separate groups, right? We're taking 18 and we're dividing them into 3 separate groups. What is that going to look like with our base 10 pieces? Actually, let's do this. It's going to look like this. Right? We took the 18, and we put them here, here, and here. Each group got 6. So again, here's a group, here's a group 2, here's a group 3, right? And each of these now is saying there's 6 units in each group. And so that's what we're going to put up here in that ones column, because 6 times 3 is 18, and we end up with a remainder of 0. So, and maybe you've never even written it like that, and normally I don't either, but I think it helps illustrate the real idea what's going on behind the scenes in long division. 3 is going into 378 at one time. It's going in 100 times, right? We're just sticking it in that hundreds place, okay? And so what we end up with here then is an answer of 126. 378 divided by 3 is 126. And you can see, again, each of these groups has 126 pieces. 126, 126, and 126. So our content standards that this aligns with the Common Core is this. And I want to point out one very important line there. Again, by grade 4, students need to be able to find whole number quotients and remainders with up to 4-digit dividends, 1-digit divisors using strategies based on place value, properties of addition, relationship between multiplication and division. And then this is the one I wanted to point out to you, right? They need to be able to illustrate and explain the calculation by using equations, rectangular arrays, and/or area models. The things that we're just doing now, they need to be able to explain that, do it like we just did it, and explain why they work. That's some pretty deep level, high level thinking, right? Because this isn't necessarily easy, but that really gets down to the deep understanding of it, okay? So the next one that we'll do here is 336 divided by 12. And we're going to do this one differently. So you still want your base 10 pieces, but the way that we're going to demonstrate this is not by separating them into different groups, but by using a rectangular array. Okay, so we're really going to be using like an area model here where we put them into rectangles. So this is one of those times where I might challenge you to even see if you can figure out what that might mean. I'm going to scroll back up in my notes here because we did this way back, it was after the dump truck, right here, right? We did 48 divided by 4, and we used a rectangular array to do it. Now we have much bigger numbers, 336 divided by 12. See if you can play around with your own base 10 blocks and make a rectangular array that could help you solve this problem. And then see if you can link it to long division as well. So I'm going to let you pause and work on that. So let's see how that's going for you. Okay. So the way you probably would start with this is laying out your base 10 pieces, and they would look like this. So that we all agree that's 336. We have 3 hundreds, we have 3 tens, and we have 6 ones. If we write this out using long division, we would write 336, and we're going to divide it by 12. 12 is the divisor. So when what we need to do here is start by building a rectangle that has one dimension of 12. Now I'm going to sketch this out because I think if I just put the array up there, sometimes it's not always as easy to see when it's all designed for you. And so the way that you might do this is you say, all right, I'm just going to sketch one of these flats, right? So right, we've got all our horizontal and vertical lines. So that represents one of those. So I know that that has a dimension of 10, okay? But what I really need, because I'm dividing by 12, is I need to add on one of those flats down here and then another flat down here. Because this then would give me the extra 2 that I would need to make 12. So by stacking those, we now have a height on a rectangle of 12, okay? So this is starting this idea, right? But what we're going to do is see, we've got all of these pieces. So this takes up, well, 10 by 12. So how many pieces are in this one column here? 120. There's 100 plus 10 plus 10. We could actually do a second version of this, right? We could do a second version of this. Another flat, right, with 100 pieces, and then 2 more longs down here, each with 10 more, right? So we have 120 here and 120 there. So what we have now here is really like 2 10s going all the way across. So this is 2 10s. We got 10 here by 12, which is 20. So this dimension would be 20. How does that link to our long division? Well, where would we put the 2? Right there. Now, before I wrote 20 like that on the previous problem, I'm just going to write 2 this time, because again, I've got 2 10s this way in my array. 2 times 12 is 24. Now, because it's in the, there's a 0 there that I didn't write, technically, we're subtracting 240 to see what we have left from this original group. And that would be 96. 96. Some people like to just subtract the 9 and then bring the 6 down. That's okay. I think this illustrates really what's happening a little bit better. Now, let me show you the formal, fancy picture that's better than my drawing. Right? It looked like this. Okay, but you can see it's the same thing. What I drew in my little sketch here is the same thing that is over here. These are the remaining pieces right there. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 6. That's where that 96 comes from. So now we go ahead and we do the next step in our long division. So what is that? Well, it is seeing how many of those 96 can continue to fit in these stacks of 12, right? And so what we end up doing here is trying to fit, again, 96 pieces in there. You can do that in this way. 1, 2, 3, 4, 5, 6, 7, 8, right? I just drew lines instead of rectangles, but imagine 8 of those long pieces, and then you have to redistribute one of your longs into some unit pieces, and they're going to look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 8 longs and 16 units. This whole grouping here is 96, right? But each one of them has 12, right? There's 12, 10 plus 2, another 12, another 12, another 12. So again, the whole thing is 96. But what we really need to count then across the top is how long is this, right? How long is this part of the rectangle? It's 8 units, right? It's 8 units long. 1, 2, 3, 4, 5, 6, 7, 8 columns. Where does that go in my long division? It goes right here. 8 times 12 is equal to 96. 8 here times 12 vertically gives us 96 total pieces. What does that look like in our sort of in a fancy diagram? It's going to look like that, right? And so if we clean it up, what you can see again, here's the long division right there. we wanted 12 along one side of our rectangle because we were dividing by 12. And then we used our base 10 pieces to put them in as many groups as we could, right, of 10s, right? We had to put them in groups of 10 first. There were 2 of them. That's the 2. And then we had to put them in individual units, still with 12 in each column. And then there were 8 for that piece right there. So that is how we can do long division and sort of see it, right? We can see it with those base 10 pieces. So just a couple more things for this video. The division, I want to talk about the division algorithm theorem. No, that's a mouthful. The division algorithm theorem. So in the previous videos, we talked about the different properties. Addition, multiplication had like additive and commutative and those sorts of things. And closure was one of the properties we talked about. Closure with whole numbers. And just to remind you, whole numbers are starting at 0, 1, 2, 3, 4, etc. Closure means when you start with a number from that set and you do the operation, you end with a number also in that set. So closure with whole numbers works for addition and it works for multiplication, but it does not work with subtraction and addition. Subtraction and addition are not closed. So subtraction and division are not closed under whole numbers. Okay. How can we prove that? Well, we can say something formal like this. Let me extend this, it's easier to read. 12 minus 15 is not a whole number because there is no whole number C such that 12 is equal to 15 plus C. That gets to the actual definition of subtraction. Remember, subtraction was defined in terms of addition. 12 minus 15 is not a whole number because if you do 12 equals 15 plus C, C is not a whole number. So that means subtraction is not closed. Do you remember what our division definition was that we talked about earlier in this section? Remember, it used multiplication. And so here is a statement, an example, showing that 38 divided by 7 is not a whole number because there's no whole number k such that 38 is equal to 7 times k, right? 7 times k is going to give you something other than 38. So this number doesn't exist as a whole number. So that shows us that division is not closed under the whole numbers. Now, sometimes we do need to solve division problems, or we need to solve problems that involve division, even though it's not a whole number. And so we end up with remainders. The example you just saw was 38 divided by 7. So what do? Well, we say 38 is equal to 7 times 5, which gets us up to 35, plus there's an extra 3 there. And so what you'll see here is you've got multiplication and addition stated in the same, like the same problem. And so this is the remainder, right? This 3 is what we would call the remainder. 38 divided by 7 is equal to 5. And a lot of times we'll even just say R3, 5R3. That's how we state our remainders. So the fact that such quotients and remainders exist is really guaranteed by what we call the division algorithm theorem. So this is, again, one of those cases where I want you to pause and read this and try to make sense of it, because we use variables in here. It says that for any whole numbers a and b with divisor b not equal to 0, that's saying that you can't divide by 0, there are whole numbers q and r, quotient and remainder, such that a is equal to b times q plus r. A is equal to b times the quotient plus r, the remainder. And this is important, r is, we say greater than or equal to 0, if we read it from right to left, and less than b. So just to take a moment to examine that, if we look at this statement there and we flip it around, notice how the big side of the sign keeps facing the r. R is greater than or equal to 0. That means our remainder always has to be positive, or if there is no remainder, it can be 0, right? That's if we do 35 divided by 7. It's just 5. There is no remainder there. But r can also be less than b, which means the remainder always has to be less than whatever our divisor was. Okay, we can never have a remainder that's bigger than the divisor. An example where we could do that wrong, if I said 38 divided by 7 is equal to 4, well, 4 times 7 is 28, and we'd have 10 more to go to get up to 38. I'm sorry, I forgot to write the 7. Oh yeah, no, that was right. 4 plus an additional 10, right? If we wrote it like this, we could say 38 is equal to 7 times 4 plus an additional 10. This isn't how we would ever do division, right? Because our remainder was bigger than the number we were dividing by. And what does that tell you? Well, it tells you that this number here was not big enough, right? 7 goes into 38 more than 4 times, right? As we saw, it goes in 5 times, right? So you have to maximize your divisor, minimize your remainder, okay? So that's what this division algorithm says. And so when you're doing long division, and again, we'll take something somewhat simple here, 41 divided by 5, 5 goes into 41 8 times, because 8 times 5 is 40. When we subtract, we get 1. This number here has to be smaller than 5. Always has to be less than whatever we divide it by. So we would say this is 8 remainder 1. And that is our division algorithm theorem.